Today, we're going to pull back the curtain on the magic that powers pretty much everything you do online. We're talking about parallel database systems. These are the unsung heroes that are somehow taming the absolute flood of data that defines our modern world. So how in the world does it all work? Let's dive in.
Seriously, just think about that for a second. You're checking your balance, but at that exact same moment, millions of other people are depositing checks, applying for loans, paying bills. How does one system possibly keep up with all of that at once without just melting down? Well, the secret is, it's not one system at all.
And that really gets us to the heart of the problem, the unbelievable scale of data today. You know, the old way of doing things, just getting one big, powerful computer to handle everything, has totally hit a wall. It just can't keep up anymore.
To really get why, we have to talk about cost. And in the database world, cost isn't just about dollars and cents. It's a measure of resources. How much processing time, how much disk activity, how much data has to get moved around. And the strategy you use to answer a question or a query can make a huge difference in that cost. And this slide, wow, it shows just how massive that difference can be. I mean, look at this. Strategy B, the old school centralized way, has a cost of 23,000 units. But strategy A, the smart parallel approach, costs just 460. That's not a little better, that's a whole different universe. We're talking nearly 50 times more efficient. It's a total game changer.
Yeah, that huge cost difference really shines a light on all the problems with the old single computer model. These systems are just plagued with issues. They have massive overhead, they struggle to keep data consistent, and they just don't scale when you need more power. And the real kicker? That single point of failure. If that one machine goes down, poof, everything's gone.
So, if one giant computer isn't the solution, then what is? Well, the answer is to completely change the way we think about the problem. It's time to go parallel.
And this is the fundamental shift. Right here, instead of throwing a huge problem at one machine, you break that problem down into smaller pieces. You distribute the workload across a whole team of machines that all work together at the same time. It's basically teamwork for computers.
So what a parallel database system really is an interconnected network designed to attack a problem from all sides at once, with lots of processors and lots of disks all working in concert. And the benefits? They are huge. Performance just skyrockets because you're doing so many things at once. The scalability is incredible. If you need more horsepower, you just add more machines to the team. You get fault tolerance built in. If one computer fails, it's no big deal. The others just pick up the slack. And it's often way more cost efficient because you can use a bunch of cheaper computers instead of one outrageously expensive supercomputer.
Okay, but going parallel isn't quite as simple as just plugging in more machines. There are a few different ways you can design these systems, what we call architectures. Let's talk about the two main flavors, shared memory and shared nothing. Here's a good way to think about it. A shared memory system is like a bunch of chefs working in one big shared kitchen. Communication is super fast because everything's right there, but after a while they start bumping into each other and it gets crowded. A shared nothing system, on the other hand, is like a massive restaurant chain. Every chef gets their own private kitchen. It's insanely scalable. You can just keep adding new restaurants. The catch is that all those separate kitchens need to coordinate perfectly to get the orders right. And then there's a third, hybrid option called shared disk. In our kitchen analogy, this is like each chef having their own personal workstation, their private memory, but they all share a giant central pantry and refrigerator, the disks. It kind of tries to get the best of both worlds.
Okay, so we have the blueprints, the architectures, but how does the system actually do the work in parallel? Well, there's a whole playbook of strategies that make it happen.
First things first, you have to split up the data. You can't work in parallel if everything's stuck in one place. You could do it round-robin style, kind of like dealing cards to each computer, or you could use hash partitioning to make sure similar things end up together. A really popular way is range partitioning. You know, all the customers with last names from A to M go to server 1, and N to Z go to server 2. Simple.
So, once your data is spread out, you can run the query itself in parallel in a couple of ways. The first is called intra-operator parallelism. Think of this as one big job, many workers. You take a huge task like sorting 1 billion names, and you give a piece of that job to every processor. The other way is inter-operator parallelism. This is much more like a factory assembly line, where different steps of your query are happening at the same time on different machines.
And you can see that assembly line right here in action. See how two different operations are running at the exact same time? And as soon as they have any results, they don't wait. They immediately pipe that data to the next station in the line, which starts its job right away.
This pipelining is what makes it so incredibly fast. There's no waiting around.
So, I know these concepts can feel a bit technical, but I promise you, they are the absolute foundation of the services you and I rely on every single day.
Ever booked a flight online? Yep, that's a parallel database juggling millions of seats. Use Google Drive or Dropbox? That's a parallel system keeping all your files safe across thousands of servers. Weather forecasting, online shopping, your cell phone company, they all run on these incredibly powerful distributed engines.
So what this all boils down to is this. Parallel database systems are the solution to the problem of scale. They are the reason we can dig through mountains of information, terabytes, petabytes of it, and get the answer we need, not in days or hours, but in the blink of an eye.
Which leaves us with one last big thought. We've managed to tame today's data deluge with these parallel systems. But as the world keeps generating more and more data, growing from terabytes to zettabytes, and who knows what's next, what new idea, what new architecture are we going to have to invent to handle the data deluge of tomorrow?